again, so we're going to continue with integer representation. Just if you walked in late, if you haven't emailed me about coming to the test on Wednesday, please do so. Otherwise, you will not get information on where is it. Second part is one more thing. So there was a couple of questions that were coming on via email that I'd like to address. So there was one question about the test. Do you need to say import NumPy as an MP or whatever module that might be? Yes. Okay. So it shouldn't be difficult once you actually put all of the you basically, even if you write your solution, you will see what are the functions that you're using, so you can quickly add this import command. I do want you to keep it in mind. Okay, so that's why I'd like you to enter, unless I actually give it myself already within the problem. So that could be the case. So second question that was coming in that I have it written. So if you see a file, and sometimes there will be like in the way the file is printed, so you need to read the file, ignore some starting lines, and then start reading the numbers. And let's say that you see an empty line in that process. So trick question is, do you need to read that empty line? And the answer is yes. It sits there empty, you don't see anything printed, but spaces, okay, and next line symbols, they're not visible on the screen, but they're in the file, and you do have to read them. That's the reason. Okay? So if you see line of text saying something, and then an empty line, and then another line of text saying something, and then numbers start, you effectively have to read it three lines with that read-line command. Okay. So those are the questions that just came up. Okay. Let's continue with integers. So we have started the question about integer and real number representation on the computer. So we always have to, or computers behind the scenes have to know what are they storing and where. And the format of what's written to the disk changes accordingly. So essentially, we are used to decimal system, okay? Essentially, because we have 10 fingers, so that's how we start changing. So you go 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, and then you gotta start again, 11, 12, right? So essentially, that came about because we have 10 fingers. Well, computers don't. And what computers work with is on or off. So they essentially work with 2 fingers. So you can count 1, 2, and then you have to start again, 3, 4, and so forth. So you have to change, but there's no digit 3 and 4 in the system that has only 2 fingers available. So we have to work with essentially zeros and ones. So one thing that we need to notice is that in decimal system, and we kind of inherently know it, we don't even think about it, 158, the reason why it's written with 3 digits, is that it's 1 times 10 to the power of 2, plus 5 times 10 to the power of 1, plus 8 times 1, which is 10 to the power of 0. So I'm working with powers of 10. In the same system, in the same way, I could actually do that with any other what we call base. This is base 10, but I could actually represent all of the numbers. You just tell me the base, and I'm going to give you the representation. And the way it works is that if I look at the number 158, I find the largest number, the largest power of 10 that fits into this number. And how many times? So in this case, it's 1, 3, 5, 8. So it's between 100 and 1,000, right? So 100 is my largest power that fits in, and I just figure out how many. In this case, 1. In case of 258, there would be 2 times 100. Right? So in this case, it's 100, and then I remove that. So what I'm left with is 58, and then the largest power of 10 that fits into that number is 10, and 5 of those. And then 5 times 10 And then I remove that, so I'm left with 8, and then that's 8 times 1. And that's how I'm actually representing this number with using digits 0 through 9, which is what's available. These 10 digits are available in decimal system. So if I wanted to translate this to base 8, what would I do? What are the powers of 8? 1, 8, 64. Okay. So those are powers of 8. So what is the largest power of 8 that fits into 158?
2.
Power of 2. So that's 64. How many of those can I fit in?
Say that again.
How many of 64s can I fit into 158? 2. So I have 2 times 64, which is 128. What's left is 30. So then I have 128 plus, and then what is the largest power of 8 that fits into 30? Power of 1, which is 8. How many of those? 3 times 8 is 24. Okay. And then what's left is 6. And that's 6 times 1. So what are my digits in base 8? 236. Okay. So basically, and if I did base 2, can you do a piece of paper and what would you get for base 2? And don't forget to include the zeros where appropriate. What did we get? I'm still working on it.
One zero zero 1 1 1 1 0.
Okay, let me see. 1 0 0 1 1 1 1 0. So it's 1 times 128, and then I have 30 left. Okay, there, no 64s in there, no 32s, so that's 0 0. And then I can fit a 16. 30 minus 16 is 14 left. Okay. Then 1 8. Then there's 6 left. Then a 4 and a 2. 0. So where you don't have a power, corresponding power, you put in a 0. Just like number 101 in the decimal system is 1 times 100 plus 0 times 10 plus 1 times 1, right? Same idea. I can come up with any base. Most of the time we work with bases up to 10, and there is actually base 16 that is used. But then I run out of digits, so I really have only 10 digits in our regular system. And then after that there's A, B, C, D, E. So essentially, those are so I can work with any base. Okay, so now what do we do with number such as a real number 0.0054. What we said is essentially there's this format. First, I have to work with scientific notation, okay? And it is worked on in base 2, okay? So then you have something like a format 1 plus p plus 2 times t, and then those two numbers, and p and t is what I actually end up storing. So first I come down to scientific notation, and then I have to figure out, given certain space in a computer, how am I going to store this? So typically for a single precision, where I'm using 32 bits, I'm going to do 23 bits for mantissa, and 8 for exponent, and 1 for sine, and then in double precision, I split that up differently. Now, before we actually, just to give you some idea about accuracy of this representation, I want to actually work it out in a very simple case, and I'm going to talk in terms of decimal system, but the concepts remain the same, and I want to switch to writing on the screen for that. So just to explain a little bit, what are the gaps in this representation? I'm going to assume for a moment a very simple, so this is representation of real numbers. So I'm just going to assume simple case in decimal system, with the understanding that computers do work with binary system. That's decimal system. So assume that I do have a scientific notation, and I have number only one digit for the. So when I do scientific notation, I do it with the number that is larger than 1, and that it's 1 point something times 10 to something. And I'm going to put these digits that I'm storing as d1.d2, and let's say that I'm storing only one digit for the d1.d2 and no other digits, okay? So I'm simplifying things. In reality, I do more, but I don't want to write all of that. Whatever it is, in reality, I have a limited number of digits that I can store, okay? So I'm just going to pretend that it's only these. And then I also have signs, so my exponent can have a sign and my number can have a sign, okay? So this is signs for the number and exponent, and these are my digits, okay? So again, it's a very simplified case, and let's say that this is all I'm trying to store. In reality, there will be more digits, but conceptually, nothing will change. So what now happens? What is the largest value if I'm in this limited system? What is the largest number, and I'm in decimal system? What is the largest number I can store? I'm obviously limited. So I put the largest digits I can, which is 9 in decimal system. Okay. And I put them everywhere, and I use positive signs, right? So my largest value in absolute case, the largest value, is 9.9 times 10 to the 9. Positive, largest positive value. What is the smallest positive value? That is larger than 0. I put the negative in the largest exponent I can, right? So that's dividing by 9. And then the smallest, I'm not going to put 9.9, but I'm going to put 1.0 because I do have to be larger than 1 for scientific notation. Okay? So I can do 0 and then this number. Anything in between, I cannot do. Okay? So if a number 10 to the minus 12 shows up, I can't store it using this storage system. Do you see that? And also if number 10 to the 12 shows up, I can't store that either because it's too big. And that's the limitation of having limited number of digits that I can store for either exponent or the main number. Okay? And similar for negative values. So my largest negative value is negative versions of this, right? 10 to the minus 9. So this is for positive and for negative. My smallest positive value is plus. My smallest negative value is negative version of this 9.9. Because sign is plus or minus. So when I actually put that on a real number line, okay, I can do 0. Okay, and I'm going to, this is not to scale unless it's approximately log scale, but I'm going to put this 10 to the minus 9 here and minus 10 to the minus 9, which is obviously not proportional in my world. Okay. So all of these numbers I can't actually represent on real line or real on real line. Okay. This is what I call underflow. And nothing above 9.9 times 10 to the 9 on my very bad log scale. Nothing below or nothing above, that's overflow. But better yet, okay, so I can do 1.0 times 10 to the 5, 1.1 times 10 to the 5, but 1.15 times 10 to the 5, I either have to round it up or chop that 5 off. Typically it's rounded up or rounded. So there's all these gaps, okay, in precision. So for all of these that is here, I have gaps in representation. Okay. Essentially, this green is a very poor choice of color. Essentially, or my 1.15 times 10 to the 5 and 1.16 times 10 to the 5, they both get into 1.2 times 10 to the 5, okay? I cannot represent them correctly. They have to be rounded up. And that's because I don't have enough digits to do so. Now, in reality, it's not that bad, and we often don't notice because we have much more digits than just one. Okay. But this is just to show you how you actually have gaps in representation. Okay. So in reality, I have more things that I can store, so it's not that bad, but I do have gaps, okay, and that can affect accuracy. So this is so-called round-off error. So no matter how many digits you're storing, if you have P that has all the possibilities after the decimal point, right, you're not going to be able to represent it correctly. Okay. Now there's one more thing that we have to, so again, real numbers I store with either 32 bits or 64 bits, and I have to decide what part of this storage, 32 bits and 64 bits, there are two of them that are there for sign, okay? And then I have to figure out this mantissa, the scientific notation, how much storage I'm going to devote to that, and how much to exponent. And that's where we actually get in limitations on what can be stored. So give or take, and again, this is just hand waving. I'm not going to go into detailed, if I can go to sketchbook, save. Open. So in a 64-bit number, okay, I'm going to use 1 bit for sign of the main number, 52 bits for mantissa, and then 11 bits for signed exponent, meaning that 1 bit of those is going to be sign and the rest are going to be the size of the exponent. So technically, if you have in scientific notation in base 1, the largest thing that you can do is something like this, times 2, 2, and then there's this signed exponent, which I have the sign, largest sign you can do is 2 to the 11 minus 1, which is 103 in base 10. And we have 52 bits to store these. It's from this calculation that in decimal system you get something like approximately 1.8 times 10 to the 308 is maximum real number I can store. So again, this is not exact calculation. I'm not attempting to be exact. I'm just telling you that given these constraints, this leading one we never store, so we use the 52 bits for all of the rest because there's always a leading one by the rules. Okay. And then so this gives me some number, and then there's exponent 2 to the exponent, and the largest exponent I can do when translated to decimal system is 1023. And that roughly, when you sum all of that up, you will get the number that is in this 10 to the 308 range. Okay? So this is just to explain where these limits came from that we had in the slides. Okay? There's this list of limits. So double precision is what I just exemplified. That's with 64 bits. So approximately 1.8 times 10 to the 308 is the largest number you can do. So if you want to do 10 to the 408, you can't do it. Okay? There will be a so-called overflow. What will computer do underneath? It might actually map it to something called INF, infinity, that is typically there or implemented in most computers, but that causes trouble in your workflow. It's going to show up as garbage in most of your computations, so you have to be careful about that. And then this is, again, so this is this underflow and overflow in the range. So if I have single precision, then I'm much more limited. It's about 10 to the 38, and equivalently 10 to the minus 38 in terms of the small numbers here. Okay. Again, I expect you to roughly know or have these somewhere on your, this is for exam 2, okay? But I expect you to have these on your cheat sheet so you can evaluate something like this. Can we get this? Yes. So that's 64 bits. Single precision is using 32 bits. And it might be, it's a choice of storage where it doesn't come about. So I do a simulation on sort of a cube that is 1,000 by 1,000 by 1,000 in size. So it's a three-dimensional volume that is discretized into 1,000 by 1,000 by 1,000 when I'm doing an algorithm. That is 10 to the 9 points. 10 to the 9, if I'm just using 1 byte per point, that's 1 gigabyte. If I have that many numbers that I want to store, and I'm using just 1 byte for them, it's 1 gigabyte. If I'm using 2 bytes, it's 2 gigabytes. But if I'm 64 bits, is how many bytes? 8 times 8. 8 bytes. So if I'm using 8 bytes, that's 8 gigabytes. Just to have that data read in, just numbers. So working memory of most of these laptops that you see open is 8 gigabytes. So I can't, on a laptop, do any computation. I can just read it in and look at it, if I can look at it. Okay? That's limited. Therefore, in that case, if I was storing numbers for this particular case or was trying to look at it, I would store it in single precision because that's twice less. So I can actually read it in and do something with it. Okay? Those are the limitations. 1,000 by 1,000 by 1,000 in terms of reservoir modeling, it's nothing. It's very small. Our reservoirs are much bigger than that type of representation. So you have to suddenly have supercomputers just to read in the data, let alone do anything with it. So that's where this storage, whether I'm using single precision versus double precision for a real number, it becomes important. And normally you don't think about it really day to day because kind of storage is around and it's relatively cheap, except when you have to put it all into your working memory. Now, why you don't really think about memory issues is that most of the time, let's say you're listening to the music. When you're listening one song at a time, you don't have to have them all in memory at the same time. You could just go sequentially through songs. Or your songs could be stored on Spotify somewhere on the cloud, right? So Spotify is thinking about that. You're not. But if you wanted to do something with all of your songs that you have, I'm not advertising Spotify here. I'm just giving an example, okay? Whatever it might be. But you rarely, even if you're mixing songs, you're not going to be mixing 1,000 songs, working with 1,000 songs at the same time. Maybe you're going to do 5 or 6 at a time. You don't have them to have them in memory all the time. But in petroleum engineering or any kind of engineering, you might need your entire reservoir in memory at a time if you want to do something. So that kind of storage and which types of numbers am I using to actually store becomes really important. And often you will have to read in chunk by chunk. So if you have too much data, you will actually read in parts of your reservoir at the time and then leave the rest be. And you have to figure out what to do. So this is why I want to at least introduce these issues to you, and then you will normally work with a computer scientist to address those issues. Now, if I have a single precision, can I represent number 4 times 10 to the minus 90? Let's go to the limits. Single precision. What's going to happen? Going to be in this underflow. I'm way smaller than 10 to the minus 38, roughly, that I can actually store. So I'm somewhere in between 0 and that 10 to the minus 38 here for single precision. So I'm somewhere here, right? And I'm not going to be able, so that's probably going to be just mapped to a 0. And then if I have minus 3 times, so for this, I would have to use double precision. Can I squeeze this one into single precision? Can I? Minus 3 times 10 to the minus 38. Can I squeeze it in? Yeah, barely, but I can. Okay. So for that one, I could use both single precision and double precision. Okay. So again, this is just sizes. Now, one final thing that we have to think about is in the same limited world, let's say that I have 1 digit, 2 digits, it doesn't matter how many. Okay. So let's say that I have 4 times 10 to the 5. And 1 times 10 to the minus 1. Both of these numbers, individually, I can store no problem. Okay? In this limited world of having, so this is back to our simple example. Simple example of having total of 3 digits and 2 signs that I'm storing. Okay. And let's say that these are the numbers that I wanted to store. I can do them accurately. Great. Now let's say that I want to add them together. Okay. Formally, if I add them, this, I have to figure out, well, what is the exponent I'm going to use for this number? This one or that one? So that something like this. I hope I have enough zeros here. 1 0 more or less, it doesn't matter. I have to have a number larger than 1 here, but only 1 digit of it. So it has to be, I have to choose this 5 as an exponent. And then precise representation, when I add these two, is something like this. But I don't have enough digits to store this part. Right? I can only use 1. So during the arithmetic part, okay, even though these two numbers individually can be represented correctly, when I add them together, I cannot figure out both exponent and that main part of the number in scientific notation to match precisely and fit into my rule of storing only 2 digits for it, right? Because I have all of these extra digits that in this world I don't have space to store. And in that process, there will be rounding off. Okay? So even though numbers individually were correctly stored, once I do the operation, that result cannot be correctly stored. Okay? So when numbers are far apart like this, I have trouble precisely storing the result of arithmetic operation. And this could be plus, minus, dividing. Okay. So typically when I'm adding a very large number and comparatively small number, this small number will be kind of chopped off. If I also have numbers that are very similar, okay, in size, and I subtract them, I might get a number that is smaller than I can represent. So I'm and it's 0 simply because it got rounded. So adding numbers that are far apart or subtracting numbers that are close together can result in issues. And again, I'm doing a very extreme example of 1, but if I replace this with like 4 digits behind 0, you kind of see same issues. Questions? Okay. So those are certain errors, and we can't avoid them. We have to work with them. We have to evaluate them and work with them. All right. That is essentially all that I wanted to say about errors. So let's do a very quick exercise on what's called machine precision. No, this is going to be in Python. No, we're going to now start with actual numerical analysis and examples, and each and every one we're going to implement in Python. So you will basically from now, so next time, not on Wednesday, we're going to have a review class, but on Friday we're going to start with root finding, and we're going to present, well, what is root finding, and then we're going to implement algorithms in Python. And that kind of thing will continue throughout to the end of the course. So there will be a little bit of theory on the methods themselves, and then how do we implement them. So we're going to use Python from now on. We're done with the mechanics of Python, or what are the rules or syntax that we're going to use. So let's look at the machine precision. So it's a fractional accuracy. Okay? So if I have two numbers that are very close, they cannot be distinguished sometimes in this addition. So let's actually try to figure out what is kind of the smallest number, delta, that when I add it to 1, I still get a number that is different from now, 1. I know that at some point, this number, when it's too small, when I add it to 1, I'm going to get 1 because of this chop off. Now, in my extreme world of storing only 1 digit, that happened real soon. Okay? When I have more digits that I can represent, that's not going to happen that soon. So this is going to be 10 to the minus something. Well, let's try to roughly find what that would be. Okay? So basically, I want you to do a script that finds this machine precision, or reasonably close, on the order of magnitude. And that machine precision is sort of the first number you can find, and I'm going to call it delta, such that 1 plus delta is equal to 1. So if you start with delta equals to 1, obviously 1 plus 1 is 2, so that's not a good delta. But then find a little, how can you, in a little algorithm, keep reducing this delta and see how far you can go. So let's say that you start with number 1. What approach would you take? Would you do a loop? What kind of loop would you do? And this is also your kind of good exercise for the exam. It's one of the loops. So my delta is 1. If I start with 1, I'm going to call it D for short. Obviously 1 plus D, if I print it, it's 2. Okay. Now if it's 0.01, I still see it. It's 1.001. And my question is, when will this D become too small for me to actually notice the difference from 1? Which loop would you do? For loop, going from where to where? You could do it both. For loop, you kind of have to know when to use it, and that you don't know in advance. So maybe while loop is better when I don't have a closed answer. Okay? So how would I use while loop? So I'm going to start with 1 just because. So while 1 plus d is strictly larger than 1. How will I get, what would I do to get this d smaller and smaller? Divide by something. What number do you pick? 2. Cool. Yeah, print 1 plus d within that loop. Ah. So initially it's 1, then it's 0.5, fine. 1/4, fine. 1/8, I keep going, okay? And I keep going. And at some point, loop stops when d became so small that when I added it to 1, this rounding off happened, and the number I ended up with here is 1. Because I ran out of numbers in Matissa to be able to represent that correctly. Is this clear? I could have divided by 3, by 7. Again, we are roughly estimating what this number would be. So what is this d that I'm left with at the end? The d itself is still correctly represented. I have no trouble representing anything that is on the order 10 to the minus 16 in itself. It's just when I add it to something larger, okay, and I have 16 orders of magnitude in between those, I'm going to run out of space in Mantissa to represent this with the same exponent. Okay? So this machine epsilon, or fractional accuracy, is roughly 10 to the minus 16. And this might, if you have more than 8 bytes to represent a real number, it's going to be smaller. Okay? But it is something that is larger than 0. Yeah? And this is a cute little exercise for while loop. If I actually just divide it by 3, fine, we can do that. And then this number is ever so slightly different. But at some point, I don't notice the difference. Yes? Okay? All right. So I will post one more practice test tonight. And we will have a review lecture on Wednesday. Other than that, study hard. All right.